So we have today, tomorrow, and next Tuesday. Okay, so tomorrow and next Tuesday will be completely about putting as much details as possible on the singularity formation for defocusing and LS. But today I just want to take maybe an hour just to explain where the intuition comes from and why we do the kind of things that we do and why it makes sense and why it lies on a path that was, things that were initiated something like 30 years ago, and how it's exactly in the continuation of the thing that were started back then. So all I want to say, really, this first hour is just about saying completely elementary things about a problem again that has triggered a lot of works, which is just so let me tell you about the energy supercritical heat equation, and I just want to start things there. Heat equation, and I'm just in the focusing case. Okay, so what I'm looking at is simply a scalar system. dtu is Laplace. No, it's not scalar. Yeah, it's a scalar system. Sorry, it's scalar. You take u positive if you want. So I have my data, which is u naught. So u is real valued. X is in Rd. And I want to put myself, so let me remind you that I have a scale invariant. So if I have a solution u of t and x, I can make another one by considering u lambda, which is 1 over lambda to the 2 over p minus 1, u of t over lambda squared, x over lambda. And I have, and I want to put myself, so if I look at the critical norms, so if S is d over 2 minus 2 over p minus 1, I want to put myself in the energy supercritical world where S is bigger than 1, right? This is the range I'm interested in, okay? And the question I raise is, what do we know? Question, what do we know about solutions? What kind of dynamics do we know? Okay, and what kind of dynamics do we know, and what kind of techniques, very briefly, do we use? And here I really want to focus on the question of construction of solutions. There is a whole universe of classification, which I'm not going to talk about. Of course, there are some links, constructions of dynamics. I'm not thinking of classifications, which would be something different. Of course, connected, but I really don't want to talk about this. And you should think that whatever has been done here is very robust, right? The key is everything I'm going to talk about, I'm going to explain it here, but the robustness and the fact that this can be propagated to other more complicated PDEs is certainly something that has been done in the last 20 years. So what I'm going to talk about is robust. And as you will see, it will give us a hint of what to do for our problem, and eventually, and also it's related to, of course, compressible fluids. Okay, so let me start with the first question. What kind of dynamics do we know about this equation? Well, so the simplest possible wave you can construct is the soliton. Okay, so what's the soliton for this problem? It's simply you look for a stationary solution. So you say you want u of t and x to be equal to q of x. You do not allow for time. So you want to solve Laplace q plus q to the p minus 1 is equal to 0. X is in Rd. And you want to ask yourself, and you want in some sense, I mean, you don't want, okay, so what you want or what you don't want actually is interesting, but you typically want something, you would like q to go to 0, in some sense to be more precise, as x goes to plus infinity. You have to think that you are in the supercritical range, so what kind of norms exactly do you want? Maybe it's not completely obvious, you have to be a little bit more careful, but it's the rough picture. So of course, the first thing, there are two things to say. First of all, we do not understand, very far from it, solution to this nonlinear elliptic equation in general. There is a better understanding in the energy critical case when S is 1, but in the supercritical range, it's very unclear. And in fact, and there's one solution, of course, that you can understand very well. So there is, of course, if you want a simple case. But this will already tell us a lot about the kind of things that we have to do. So a simple case, of course, is that I will assume I'm just looking for solutions with radial symmetry. Okay, so if I do that, I just get myself, so it means that I'm going to call R, it's the modulus of X, then this becomes completely trivial. So this is just an ODE problem. So I have Q double prime plus D minus 1 over R Q prime plus QQ to the P minus 1 is equal to 0. And of course, this is particularly simple because you have to remind yourself that you have a scale invariance in this problem. So if Q is a solution, I can make another one by letting scaling act on it. Okay, which means what? Which means that the value of Q at the origin is irrelevant, so I can always assume. So this is just an elementary shooting problem. So I have Q double prime plus D minus 1 R plus QQ to the P is equal to 0. And in fact, I can, so Q prime of 0 must be equal to 0. This is regularity. This is necessary. But in fact, using the scale invariance, I can always assume, say, that Q of 0 is 1, or whichever constant I want, just using the symmetry group. Okay, so in fact, the only question I need to ask myself, so in fact, there is a unique solution. So if this is R, if this is Q, I'm starting here, and the only question I need to ask myself is, where does this solution go? Well, so you can look at your radial ODE in the eye, but in fact, the correct way to think about this, it's not very clear what's going on here. And this is, I'm showing you this for a very simple reason. You see, this seems to be a completely trivial ODE equation. It is a completely trivial ODE equation, but already this question is already containing the notion of being supercritical. Right? That is, the fact that my scaling is bigger than 1 is essential, because actually, if S was less than 1, the picture that I'm going to draw, the way these things behave, would be completely different. So, and you have to think that on this problem, it's completely trivial to see this. If you start making a more complicated problem, of course, maybe it's not so trivial. So how do you address this? Which is the simplest way to address this? And this will come back, of course, when we will study compressible fluid. This ODE is not very pleasant in this form. You don't understand anything. You do understand everything if you change variables and you do a so-called Emden transform. And that's something extraordinarily powerful that we're going to do later. So what's the Emden transform? So I wrote this here. So you define U. I'm sorry. So this is Q of R. You change variable. You define Q to be V of R divided by R over 2 over P minus 1. And you declare that S is log R. OK? So you do your algebra. And what you will realize is that the equation for V, so now prime is DDS. You see exact, so V prime is dVds. And what you get is exactly this. You get V double prime plus twice S minus 1 V prime minus C infinity to the P minus 1 V plus V to the P is equal to 0, where C infinity is the number, so it's 2 over P minus 1. You have D minus 2 minus 2 over P minus 1. The whole thing is to the power 1 over P minus 1. OK? So I claim it's completely equivalent. And you immediately understand what's going on here. So S is just critical scaling. It's exactly D over 2 minus 2 over P minus 1. So this number C infinity depends on nonlinearity and dimension. It's whatever it is. It's well defined in the energy supercritical range. And you see immediately what's going on here. You've transformed. Yeah, please.
S is a probability.
S is defined 2 times. I'm sorry. This is a disaster. So let's call it X. Thank you very much. Let's call it X. This is ddx. I'm absolutely sorry. Okay. X is log R. Okay. Later it's going to be X. Right. S is my scaling. Okay. sorry. So this S is a number. You're absolutely right. It's the number. It's the number that shows up there. Okay, and this is X derivative. Thank you, Claude. So what I did is I transform a non-autonomous ODE, because of course my ODE here depends on R, into something that's autonomous now. There is no dependent. I just depend on my variable. My coefficients, none of them depend on the new space variable X. Okay, so it's much simpler. And you see immediately, it's very easy to see. Of course, if you compute, the study of this is completely elementary, because if you form J of X, which is exactly, so V prime squared over 2 minus C infinity to the P minus 1 over 2V squared plus V to the P plus 1 divided by P plus 1, then you will see immediately that the derivative of J, so J prime if you want, is nothing but minus twice S minus 1, I suppose it's V prime squared. Right, and you see exactly what's going on. Of course, when S is equal to 1, this is the energy critical case. You have a first integral, and actually you have explicitly the solution. And when S is bigger than 1, you have dissipation. So you will be asymptotically attracted to the infimum of J, which you can show is exactly the limiting value. So the attractor is simply the solution. You just take V constant, so it's simply V is C infinity. Okay, and then the only thing that remains to be done is to understand, it's the key. These Emden transform, they tend to make your problem singular in some sense. So what do I want? At the origin, I want Q. I want a nice function, right? I want Q of 0 to be 1. Okay, so my boundary value is just at the origin, I want V to be equal to 0. Okay, and this is at S going to minus infinity, and this is X going to minus infinity because this is X, this is R going to a 0. Okay, so my Emden transform has changed my variable. So what I want at minus infinity, which is R equals 0, I want V to be 0. So if you think, you should think of it this way. So what you want is that you want J of X to go to 0 as X goes to minus infinity. That's where your regular solution sits. That's the condition of regularity. Okay, so the picture, if you want, is the following. If this is the function of X, if this is J, what you will have is the typical Bassan of attraction. So you start here, it's decaying, and you can show that you will be asymptotically attracted to the unique infimum, which is there. So it means that the unique smooth solution that starts here is going to be attracted there. Okay, and it's completely trivial once you've changed variable and you've put yourself in the formulation of the Emden transform. So what is the outcome? The outcome is that when S is bigger than 1 and you see your numerology arise, you see these guys show up. When S is bigger than 1, then indeed, what will your solution look like? Well, what you have is that V is attracted to this value C infinity. So it simply means that asymptotically you converge. So it means that Q of R will behave exactly like, so V goes to a constant, which I call C infinity. So I behave asymptotically like C infinity over R to the R over 2 over P minus 1. Okay, so which is typically, so of course, it's not any decay, it's something very specific. It's what is called, so I have, maybe I can write it here, I have Q of R that decays like C infinity over R to the 2 over P minus 1. So I have decay, and this is not any decay, this is self-similar decay. This is self-similar decay. Okay? So this is the soliton. So you see immediately, so the point of showing you this is just to show you that immediately as soon as you start trying to have special wave for your nonlinear problem, well, immediately, if you're lucky, it can turn to ODE, but the study of ODEs, you need to work a bit, and if your ODE is a PDE, then, you need to maybe work more. Okay, but this is a typical illustration, and this is an illustration where you see numerology arise already. Maybe it's not completely clear at the level of this equation. It's crystal clear once you've done your change of variables. Okay, so this is the first thing. So this is the typical, so this is a first kind of wave that you can think of, soliton. So they are there in the supercritical world. Second kind of solution that I would like to construct is self-similar solution. Okay, so here I want to do something that we will do that is absolutely central in all the question of singularity formation, which is dynamical rescaling. Right? So dynamical rescaling is simply this idea that there is no way, you do not study singularity by staring at the initial problem. You need to change variables. You need to zoom on what you expect, zoom on the expected singularity. In other words, you're looking for something big in a way or another. So what you do, you will normalize, hoping that you've captured an object which is maybe non-trivial. So what I will call the self-similar equation is obtained as follows. And again, I'm going to do this on the heat equation, and then we will, just because it's so much simpler, and then it will be the same on LLS. Okay, so what's the self-similar equation? So what do I do? It's very clear. I simply use the scaling of the equation, but I want to do this dynamically. Okay, so what I say is the following word. So I want to solve dtu equals Laplace u plus u to the p minus 1. So u is the function of t and x. And what I do is I change variable. I ask for u to be equal to 1 over lambda of t to the 2 over p minus 1, some function v of s and y. And s is the renormalized time, which is defined by ds dt. So it's up to a constant. So ds dt is 1 over lambda square of t. Okay, so this defines s. And y is the renormalized space. I'm sorry?
You call it Z. S.
Sigma. X, si tu veux. Là, c'est le problème du S. Ou alors tu changes.
Well, no, but S is my. Forget about this S. It's because I know what you want. So I know. I'm sorry. Let's call it tau. Okay, fine. Okay, tau is my renormalized time. Okay, so y is x divided by lambda of t. Okay, so it means that, of course, the idea behind this thing is obvious. It's just that what you have in mind is that what you want, you have a scale invariance in your problem. So you have a feeling that maybe the scale invariance play a role, and it will play an essential role. And of course, the way you want to form big U is by thinking that this scaling parameter is going to go to 0, right? That this will create, of course, space will be dilated, so it means that there is a zone of concentration, x of size lambda of t, if you want, and you will form the singularity. Something singular happens because maybe this function v will not be trivial. Okay, this is exactly the mechanism. So this is really the expectation, if you want. The way singularity will arise is because lambda of tau, if you want, is going to go to 0. So maybe this is lambda of t. For the moment, this is going to happen at some time big T. T will be the blow-up time. And then the expectation is that, but this is typically what you expect. So if you do this, okay, so you do this renormalization and you ask yourself, what happens with my equation up there? So it's very easy. So you have dtu is Laplace u plus u to the p. So this part is easily computed because this is just scaling in space. Y is x divided by lambda of t. This Laplace is in x. So if I compute this, so I have 1 over lambda to the 2 over p minus 1. Because this is just my renormalization, I lose 1 over lambda square because it's in x, and I have the Laplacian in y of v. So this is the first term. And this term is just going to be plus 1 over lambda to the, in fact, I have 2p over p minus 1, v modulus of v to the p minus 1. Okay, and of course, these two exponents are equal. This is exactly how you compute this number 2 over p minus 1. So this is exactly 2 over p minus 1 plus 2. It's meant to be. Okay, so this quantity is easily computed. It's just 1 over lambda to the 2 plus 2 over p minus 1, Laplace v plus v to the p minus 1. That's just scaling. Okay, it's just the way you chose the 2 over p minus 1 here. Okay, but then you need to compute dt. So dt is just computed there. So now you compute dt. So that's an easy computation. So what's going to happen to you? So when you compute dtu, so first of all, you have the time dependence. So you have 1 over lambda to the 2 over p minus 1, which comes out. And then you have two terms. You have the term that comes from the fact that you let dt act on v. But of course, ddt is dds dd tau. So it's exactly 1 over lambda squared d tau v. Okay, and then you have a term, of course, that sees, you have to be careful here. You have 1 over lambda to the 2 over p minus 1. You have v of tau, and it's x over lambda of tau. Okay, so you have one term that sees the fact that you're taking the derivative here in tau. So this term is going to give you exactly, so you have minus, so because it's a minus because you dd tau here, and you have minus 1 over lambda squared. And I prefer to compute derivative in tau time, so I'm going to have exactly this. D lambda d tau times 1 over lambda. And then I have the operator. So of course, I have two such terms. I have one term when I take the derivative here, and I have one term when I take the derivative here. So my final operator is 2 over p minus 1 plus lambda v, where I define lambda. Lambda v, it's simply, it's y scalar nabla. It's sort of Fokker-Planck, if you want, thing, which just comes from the derivation of this term here. So I want to write everything in terms, so this is equal to 1 over lambda to the 2 plus 2 over p minus 1. So this is d tau v. So I'm going to know, so because it's impossible for me, so this is, when you see lambda tau, it means d lambda d tau. Okay, this is going to rise all the time. I'm going to do this. So when I index by tau, it just means that it's the derivative. So my equation is exactly this. So I have d tau v. I have minus lambda tau over lambda 2 over p minus 1 plus lambda applied to v. So this is, if you want, this is the scaling drift. Okay, and I have and I'm sorry, and I have 2 plus 2 over p minus 1. So this is the dt time. Okay, so it's just a simple computation. So what do I call the self-similar equation? So the self-similar equation is the following guy. It's exactly, so it's this PDE, so it's d tau v equal Laplace v plus v to the p minus 1. And then I put this term over here on the right, so plus lambda tau over lambda times 2 over p minus 1 plus lambda applied to v. Okay, so this is my new flow. This is what I want to understand. So it's completely equivalent to the original flow, right? There is a one-to-one. I know exactly what I've done, but there is a point here. So what's the expectation? So of course, these are things that you need to prove at the end of the day. The expectation is the following. First of all, something that is essentially automatic. You started with a time t, which you expect will be in some 0t, and typically I'm going to talk only about finite time blow-up, so t will be finite. And this will typically push for a reason that need to be, I mean, it's part of the analysis, but you should think that the tau time, the renormalized time, will be in some value turn out plus infinity. Okay, so it's typically a global time. Okay, so I transform, this is what I want to think, and I transform a finite time blow-up problem into a global existence problem. Okay, what I want is I want to make this solution to this equation live forever. That's target one. The second thing I want, you have to understand, the second thing I want this is a ridiculous transform. I could do that for the linear problem if I wanted to, right? If I do this for the linear problem, I can do this transformation, but I know exactly what happens if I force lambda to go to 0. Then, of course, solution to the linear problem, they do not blow up. So V is just going to go to 0 even further, even faster, right? So what I want, my aim is to ensure that V of tau and y does not disappear or vanish as tau goes to infinity. Right? This is my target, because you see, I will force lambda in a way or another to go to 0. I want V not to disappear, because if it disappears, it's like in the linear situation, I'm not doing anything, right? So this is my aim, and this is how all singularity formation problems find their way through in a way or another. I want to find a global in time solution to this thing that does not go to 0. That's my target. If you can do that, in a way or another, you form a singularity. Okay, so now you have a problem, which is a very classical problem. You have to be very careful. So what is non-standard and what makes... So I want to stress this immediately, because this is not a remark, this is essential. So there is always a problem, which is not a problem, it's the heart of the analysis. You know, I started with a u, which is supposed to be a nice function. So this is x, this is u of t and x. Well, I don't know what it looks like, but I typically expect that it will form some sort of singularity somewhere. And then I mapped it on this, you know, with this, and in particular, I define y to be x over lambda of tau. And I typically think that lambda of tau is going to go to 0. So what does it mean? It means that y is of size 1 when x is of size lambda. Okay, so this is the size lambda of tau. So if I draw things in y, and of course I renormalized. So maybe this is y, this is v. Okay, so what you have to think is that this function, so you know, y can be very large, and I'm still, for example, x is of size square root of lambda, but y is still very large, but I'm still in the singularity. So v as a function of y, what is its behavior at infinity? Well, you have to be careful. I can allow, maybe if this is 1 over square root of lambda, maybe v wants to grow. I don't know. Because I have no idea what my solution, what's the size of my solution in here. I know that if I go super far, right, if I go here, I want to look like a u. So I know that at the end of the day, at some point, maybe I want to go back down. But there may be free boundaries. There may be a region where uv wants to grow, and then it only later discovers that it wants to go back to 0. Right, so the question of designing function space after renormalization, what is relevant, what kind of solution is relevant, what kind of solution is irrelevant, is not something that's given to you from start. You need to have an idea of what you want to do, and what kind of solution you want to do. Okay, so this is what makes this problem slightly you know, unfamiliar in the beginning, is that it's not like you're facing a PDE where you know your function space, you know what you have to do, and you know exactly what kind of boundary conditions you have. Here, it's not given to you, right? So boundary conditions, what you mean by boundary conditions in space, what you mean by admissible solutions may be tricky. You have to be very careful here. May be tricky. Okay, and precisely, it's exactly this question. What kind, you know, it's very easy to make tons of completely silly solutions to this equation. Which ones are going really to be related to the description of a singularity formation corresponded to a well-localized smooth initial wave packet? That's the problem. Okay? It's easy to make tons of crazy solutions, but which one are really the zoom of a decent solution in original variables? That's not obvious. Okay, so what is the simplest, the most stupid, simplest possible singularity? Well, it's very clear. As I said, what I want a solution to this equation that does not disappear as tau goes to plus infinity. Well, how about a stationary solution? Right? So the simplest thing you can think of is to look for v of tan y stationary. Okay, so if you mean stationary, it means that this enforces this coefficient to be constant, right? Because if it still depends on time, you will have dependence on time here. So this means that this forces you. So typically people like to normalize this by a half. And if you unfold your change of variable, it means that, in fact, lambda of t has been chosen to be the square root law. Right? Because you have to remember d tau dt is 1 over lambda squared. So I claim that this is exactly this, which can be checked. Okay, so it means what? It means that if you enforce, so this is the so-called scaling law. So this is scaling. If you enforce scaling, then this extra parameter here enters as a constant in your problem, and then you have a hope, then maybe you can, so it means that you renormalize. So if you want, you can do this from scratch. You can decide, so if I choose explicitly, so I can think of it like this. If I choose, yeah, please? It's just the square root, right? It's just the ddt. No, but you can put 1. It's just that it's the way because it's just that if you open the literature, there's always a half here. It's irrelevant. You can put 2, 3. It's just a number. Okay, it means nothing. It's just that I don't know. This is how people, probably because of the adjunction of the operator, but this is just this is the constant that has been chosen from scratch. Okay, but it's irrelevant. So if I choose explicitly lambda of t to be this, and if you want, this is exactly what my self-similar equation is going to be. So I'm going to have d tau v is Laplace v plus v vp minus 1. I have plus a half 2 over p minus 1 plus lambda v. And I remind you that lambda is the operator y scalar lambda. OK, so stationary solution. Stationary solution simply means, so this is what I call, this is what I will call a self-similar profile. Self-similar profile. So I'm going to call it maybe phi. So I simply take v of tan y to be phi of y. And phi is supposed to solve, I'm looking for phi who would solve the so-called self-similar equation. So I have Laplace phi minus plus a half, plus a half, so it's a phi, sorry. So I have plus a half 2 over p minus 1 plus y that grad phi plus phi to the p minus 1 is equal to 0. Okay, so this is the self-similar equation, and of course there is the question of boundary condition. Which I'm going to talk, which is the heart of the matter. It's not given to you. It's not clear what is relevant and what is irrelevant. OK, so say you want to solve the self-similar equation. How are you going to do something like this? So first of all, we have no obvious understanding of this equation. We do not know all solutions, far from it. Second of all, there is no obvious variational methods here. I mean, it's not clear how you can, well, there is some self-adjoint structure, but it's not clear how you can use it. But there are, this is really, you enter the world. So what you can do, of course, is reduce, like I did for the soliton. You can try to reduce to r is modulus of x. Okay, so you just look for profile phi of x that are identified to be phi of r, and you get yourself a very nice ODE. So you get phi double prime plus d minus 1 over r phi prime plus a half 2 over p minus 1 plus r dr phi plus phi to the p minus 1 is equal to 0. And of course, what you want what you want so this is really, so you think of it as a shooting problem. So this is R, this is phi, right? So you're looking for phi of 0. And now you have to be, and of course you need phi prime of 0 to be 0 because this is smoothness. You want to be smooth at the origin. But of course you have to be careful. The argument of scaling symmetry that hold for the Soliton equation. So if you remember the Soliton equation, it's just that this term was absent. Okay, but now you've put this term in the picture. It will not like, if you start rescaling, it will not like it. Okay, so in particular, this term kills any sort of scaling symmetry. Right, so this kills, so this term is a problem. It tells you two things. So you lost scaling symmetry. And if you do the Hendon transform, then you have to be careful. You will still have, it's no longer autonomous anymore, not autonomous. Not autonomous. Okay, so this thing is a pain. If you want to study this, even just the dynamical system as an ODE, it's a pain. So there's been beautiful works related to actually exactly understanding solution to this equation. So actually, because it's a scalar system, it's understood. So this has really been done by Le Pen in the 90s. This has been extended beautifully. There is a paper by Dukertz and his collaborator on this question for the wave equation, where similar things were done. So in some sense, you can understand. You can put your hands into this ODE. You have to work. There are many things that need to be understood, but you can understand solutions to this ODE. In particular, what you can show is that for P not too big, so this is the Joseph-Lundgren exponent. Joseph-Lundgren exponent. For P not too big, then there exists solution to star. So this is star. There exists solution to star. So phi, so they are smooth solution to star such that actually you decay phi of r behaves, as r goes to plus infinity as a constant which depends on phi divided by r to the 2 over p minus 1. Okay, so there are very special self-similar solutions. There are self-similar solutions which asymptotically decay like scaling. Okay, so this is what I call self-similar decay. Okay, so maybe let me say just a word. Why do I care for self-similar decay? Why is this relevant? There is one thing that you need to understand immediately. Let me make this observation. Why do I care for self-similar decay? Why is it sort of a keystone in the analysis? Why do I care that this solution, they decay like this? So why self-similar decay? Well, think of your solution initially. So you have u and t and x, and I've rewritten it as 1 over lambda to the 2 over p minus 1, some profile. So I said v of tau and y is just r over lambda. Okay, and to leading order, actually I have an exact solution, which is exactly 1 over lambda of tau to the 2 over p minus 1. So I have phi of r over lambda. Maybe this is lambda of tau. Okay, so what does this thing look like? Well, it's very clear. So this is space. So I just measure in r if you want. I just measure with my modulus here. So this is r. So this is u. And of course, lambda is going to 0. So at the origin, I am like phi of 0, which is some number. So I'm huge. Okay, so if you want on a boundary layer of size lambda of t, I'm huge. Okay, I'm very big here. Okay, so this is huge. But of course, if I fix r, so say I arrive at r equal 1. If I fix r and I let lambda go to 0, this thing will behave like the asymptotic of phi. I need to tell you how does phi behave as this thing goes to infinity. but which is exactly, so if I call this y, I know exactly how this thing behaves. It behaves like 1 over lambda to the 2 over p minus 1. But I say phi behaves like a constant divided by y to the 2 over p minus 1. Okay, but y is r over lambda. So this is exactly constant divided by r over 2 over p minus 1. Okay, so what does it mean? It means the following thing. It means that what this guy does for me is that, of course, near the origin, I'm getting bigger and bigger. But as soon as I move away from the singularity, I'm back with something that does not explode anymore. Okay, so I'm just staring. So what self-similarity does for you with the decay is that it tells you that here you become larger and larger, but as soon as you exit the singularity, you're smooth. And actually, you're drawing asymptotically a universal profile, which is 1 over r to the 2 over p minus 1. This is as r goes to 0. So it's the mechanism to connect something that's getting huge at r equals 0 with something that's, calm down as soon as you move away from the singularity. This is given to you by this decay. If you don't have decay, what you will typically have is a solution that wants to invade. It will not only blow up at the origin, maybe it will blow up faster. And maybe it can happen, but this is what self-similar decay does for you. OK, excellent. So let me just say a word, and I just want to say a word here about this, because this is absolutely essential. I just want to say a word about this. I'm telling you, I am in the energy supercritical world. I want to have a solution to a nonlinear ODE which has a certain behavior at infinity. And what I'm telling you is that, well, you can't always do that. It's not true. You need some condition. Okay, so this is what I call, and this is going to be central in the defocusing analysis case as well. There is what I like to call supercritical numerology. That's one thing. And the second thing I want to tell you, is that you can't do whatever you want. I mean, this is a shooting problem. You want a solution that is nice at the origin to behave in a certain way at infinity. So it's really a shooting problem. Which means that there are quantization, which means that you cannot choose the value of phi at 0 cannot be chosen arbitrarily. Okay, so there is a very simple way to see this. So let me just take 10 minutes to show you this, because again, this is going to feed completely our intuition when we will go to a more complicated problem. So let me, on this problem, ask myself, how can I do something simple to construct solution to this thing here? So I want to solve this. So this is the radial Laplace phi. I want to solve this plus a half 2 over p minus 1 plus r dr phi plus phi to the p. So actually, I'm going to have positive phi, so I can think of it. I want to solve this, and I want decay. So I want phi to behave like a constant, which may depend on phi, divided by r to the 2 over p minus 1 as r goes to infinity. So how can I do this in a very simple way? So there is a very elementary, so this is something that it's been known in the literature. There is a very nice sort of review on this by Bison, which sort of says exactly these words explicitly. I like this a lot. So there is a completely elementary way to construct solution just by bifurcation. What's the observation? So observation one, there is an exact solution. And this exact solution, remember when we solved this, I told you that if it's just the solution equation, I told you that you could map the solution, so you could define Q to be V divided by R over 2p minus 1. And I had this equation for v that was something like v double prime plus s minus 1 v prime plus c infinity v minus vp is equal to 0. So this thing always have a special solution. I just take v, and maybe this is because I need to, this is p minus 1. So I simply take v to be c infinity. So it means there is always a special solution to the stationary problem, which is, we noted phi star. So it's phi star of r. It's exactly this constant c infinity divided by r to the 2 over p minus 1. Okay, this thing is a solution to the stationary equation, but also to the self-similar equation because it has the correct homogeneity. That's exactly the power that kills this operator. Okay, so this is the so-called homogeneous self-similar solution. So it's a monster. It's both a soliton and a self-similar solution. Okay? So what does it mean? It means that what does it look like? So this is my exact solution. So I mean this is 0. So it's phi star. This is phi star. Okay, so I mean it. It's a certain constant divided by r over 2 over p minus 1. Okay, but then, but of course it's singular at the origin. That's bad. So now I want to understand, question, can I avoid this singularity at r equals 0? Can I do something better here, right? Can I do things in such a way that I'm going to have, I want to trade this growth here by smoothness. Okay, so there is a very simple way to do this. So you look at your equation here and you say, I want something to happen near r equals 0, so maybe I can just renormalize. Maybe I can just decide by my phi of r, I'm going to write it down as, I don't know, what I'm going to call it lambda again. I'm going to let some scaling act. So I'm going to have something that I'm going to call, I don't know, s. No, I'm going to call it q. No, I'm going to call it psi of r over lambda. So I'm going to have y is r over lambda. So it's not the same lambda, right? It's just lambda is just a small parameter. So I just zoom in this region here. Okay? But if I do that, then I know exactly what's going to happen to my PDE. I know exactly what's going to happen to my PDE. So what I'm going to have is that I'm going to have to solve Laplace. So it's going to be in y now, psi plus psi to the p minus 1. And you understand what's going to happen here. So when I take the Laplace, I'm going to have 1 over lambda 2 plus 2 over p minus 1. But the other guy, 2 over p minus 1 plus r dr, if I compute, if you want, Laplace p is going to come with a factor 1 over 2 plus 2 over p minus 1. This is going to be Laplace y in c. But the other term, the scaling term, 1 half 2 over p minus 1 plus r dr psi, this term is going to have only a factor 1 over lambda to the 2 over p minus 1. 2 over p minus 1, maybe there is a half. So I have plus y dy. This is phi. This is psi. Okay, so this is what I told you. This term does not scale. So I'm going to have a term here. I'm going to have plus a half. So I'm going to have lambda squared. 1 half plus y dot grad. Sorry, in this case, just y dy psi is equal to 0. Okay, now I have to think that lambda is very small. Okay, so this is the key. This term is here. So now you're going to tell me, okay, but that's really cool because when lambda is 0, formally, I have a very nice solution to that, which is smooth at the origin, which is what I want. I have the soliton, right? So when lambda equals 0, I have a very nice solution. I can simply take psi equals q of y. Okay, so what I would like, and this is a very standard thing, I would like to glue these two solutions, something that's like 1 over lambda to the 2 over p minus 1 q of r over lambda. I want this to be equal to maybe psi star of r plus correction. Okay, and as a matter of fact, so you're in very good shape here because remember, what is the asymptotic behavior of the soliton? so if you fix R, imagine that lambda is very small. How does this thing behave when lambda is very small? Well, it's the asymptotic of Q. But the asymptotic of Q, as we said, is exactly 1 over R to the 2 over P minus 1 as well. So it's the same asymptotic like the asymptotic of this guy. So you are in very good shape. Okay, so it seems like you can do it. Okay, so but in fact, if you want to do this, everything is in the correction. Okay, if everything is in the correction, it means that everything, you cannot understand this problem here. Right? It means that everything is in the correction. Right, so but if everything is in the correction, it means that you cannot solve. You need to understand the linearized operator close to the homogeneous solution. It's close to phi star, and actually once you have it close to phi star, close to Q, it's very easy. And you know exactly what's going to happen to you. Let me not make the details of this, but it's very clear. Look at my PDE over there. I have Laplace, it's my ODE, I'm sorry. I have Laplace phi plus 1/2 2 over P minus 1 plus R dr phi plus phi to the P is equal to 0. Okay, and now I want something that's a correction. I want phi to be phi star, I don't know, plus a correction, which I'm going to call epsilon of R. Okay, and phi star is it's my exact self-similar solution. It's C infinity over R to the 2 over P minus 1. Okay, so I want to solve this hyperterm, and I'm going to see the linearized operator close to phi star arise. How am I going to compute this guy? Well, it's very clear. I'm going to have the linearized operator, if you want. I'm going to have my linearized equation is going to be H epsilon is a nonlinear term in epsilon. And what is H? Well, it's very clear. It's just going to be Laplace of epsilon. I have this is linear. I have 1, 2 over P minus 1 plus R dr epsilon. And then I have, when I linearize here, I'm going to have plus P phi star to the P minus 1 epsilon. Okay, I just linearize phi to the P close to phi star. Okay? But then what did you get here? Well, it's very clear. You get the following thing. So you get, so H is Laplace in R plus 1/2 2 over P minus 1 plus R dr in epsilon plus, so I have P phi star, but phi star is not anything. Phi star is C over R to the 2 over P minus 1. So this thing, so if I put this thing to the power P minus 1, I get P C infinity to the P minus 1 divided by R squared is equal to 0. Okay, and now you see what's going on here. It's very clear. What is your problem? Your problem is at the origin. So at the origin, this thing, you can throw it to the garbage. It's irrelevant. It's not this guy I'm interested in. I'm interested in how does my Laplace talk to a 1 over R squared term. Okay, and then there are two worlds. It depends. It's related to the Hardy constant in dimension D, either on above or on below. Of course, this is the wrong side, right? You should think maybe you want to write minus H. So you have positive, minus, and minus. Okay, so the whole question is, what's the spectral behavior, or if you want, what's the behavior of your fundamental basis at the origin? But that's dictated by where is this parameter with respect to the Hardy constant. Okay, and this question, so in fact, P C infinity to the P minus 1 is less than the Hardy constant, which is D minus 2 over 4, I think. This is true only if P is bigger than the so-called Joseph-Lagrange exponent. So it's just, which actually is finite. P Joseph is finite if dimension is bigger than 12. Okay, so in fact, if you're below, which is the case of my theorem, this is worse than the Hardy constant, which means that you have a whole oscillatory behavior of solutions at the origin. And because it oscillates, you will be able to glue. Okay, so if you are, so when P is not too large, So you should think of it this way. Give me dimension huge. If dimension is bigger than 12, then the picture is the following. If P is not too large, then actually the fundamental basis, you have oscillations of the fundamental basis at r equals 0. And these oscillations allow you to compute, so you can compute values. In fact, you can compute a discrete sequence lambda n that goes to 0 as n goes to infinity, such that one can glue. So it means what? It means that you have a sequence, you have a sequence of self-similar solutions. What do they look like? If this is R, they look like my 1 over R, so my C infinity over R to the 2 over P minus 1. But then near the origin, they are reconnected here to something that looks like 1 over lambda n to the 2 over P minus 1 Q of R over lambda n. And lambda n is a very special sequence. It's not anything. It's a sequence that goes to 0 as n goes to plus infinity. So you have a one-parameter family of solution to the self-similar equation that has the correct asymptotic behavior at infinity. And the scale that it requires at the origin is discrete. It's a specific sequence which you can compute asymptotically when lambda n goes to 0. Okay, but this is P less than Joseph Lagrange. Because you need these oscillations, right? Because you need oscillations. So now you could ask me, okay, so it means that, this is what I mean by supercritical numerology. It means that you can compute numbers that are attached to certain nonlinear structures, here the soliton and the self-similar solution. And even in the radially symmetric case, it's not completely obvious. I mean, it took some time to understand all this. But now the picture is very clear. If you're not too large in terms, so you can compute this explicitly, then indeed you can solve your self-similar equation. It gives you a very good candidate to be a so-called blow-up profile. And indeed you can run this whole program. And I will explain later how. So you can run, but when you have these profiles, one can transform the self-similar profile into a true solution. What do I mean by that? You have to be a little bit careful here. My self-similar profile, my phi, they are like, they behave asymptotically like 1 over R to the 2 over P minus 1. I'm typically in dimension large. P is large, so this is very bad decay. So I decay very slowly. So I'm certainly, this wave per itself is not in any reasonable function space. It's not in the energy space. It's not anywhere. Okay, so I need to, it's not because I have an exact solution. It does not give me a solution to with finite energy. So what you can show, and I'll certainly it will be part of the analysis, but one can show that indeed this solution can be truncated in a decent way, and that indeed they correspond to, if I look at my original solution, so maybe in X, indeed one can make sense of the fact that in some region in space here, I very much look like a rescale version of phi star. I look like this. Maybe this is x divided by lambda of t. But of course, as I move away from the singularity, right, I'm going to be nice. This guy is not, but I don't have to stick to this guy. I can reconnect to something nice. Okay? This is part of the analysis. But if you want this is really a two-step analysis. First, you need to construct your profiles. Then you need to show some sort of stability, and you need to design a function space to achieve all this. But this is a different problem. Okay, so this is supercritical numerology. So it's telling me, so what is, so if I go back, so this is what people like to call a type 1 block. Right, so if you have a self-similar solution and it's nicely decaying, this is what people like to call type 1. Okay, so it simply means if I write my self-similar equation again, this is Laplace v plus a half 2 over p minus 1 plus write that grad v plus v to the p minus 1. So it simply means, so again, it simply means that when p is less than pgl, then this type 1 exists. So you should think that, again, simply means that the leading order dynamics of this equation is just given by a stationary solution. And there is a nice nonlinear stationary solution to this equation because I am below the pgl. OK, so now there is something that needs to be said here, because, again, it's going to be fundamental for the case of the defocusing NLS. There are two other solutions that are known. So you should think that there are cases where you know that, so typically when p is bigger than pgl. But so actually the situation is slightly different. But the strategies that I showed to construct a self-similar solution, so the construction that I showed to construction of self-similar
So if suppose you had another special solution that you know that had the same asymptotics, is there, other than the soliton and the steady, the self-similar and the steady state?
Oh, there could be. I mean,
and those ideas of gluing, would it work as soon as you have something like the tail and the dynamics are concentrated?
No, but it's super tricky. I mean, it totally depends on your problem. It totally depends. This is very far from being obvious. All this needs to be done, with. It's just one example. Gluing has been done in millions of various situations, but it's always picky. You have to, but it's about making ansatz and trying to make things that look the same be equal to one another. Okay. So indeed, so when p is bigger than pgl, the construction of self-similar solution does not work. And why does it not work? Again, because it's when you try to say, I mean, this is also, you have your singular self-similar solution. You have this guy, and you try to glue it. So this is maybe my profile. And you try to glue it here to rescale q. So you want to put 1 over lambda to the 2 over p minus 1 q over lambda. When you try to do that for the stationary problem, it fails. It fails. It fails because there is a change in nature of the linearized operator, because you lost oscillations. And these oscillations, that is, your term, because you arrive with oscillations which allow you to glue things, and you completely lost them. So there is really a change of nature in the problem. So you do not have an obvious candidate. I mean, you don't know essentially how to construct stationary solution to this equation when p is too large. Okay. So what do you do? So there is an absolutely immense breakthrough done by Herrero and Velasquez back in '94. What they tell you is the following thing. So this is Herrero Velasquez. '94. They tell you, but it's okay, because what you want to do something else. You want to do something very, very, very tricky. You see, when I want to do singularity formation, I told you what I want. I want a solution to this equation that does not go to 0. But I never said it had to be bounded. Maybe it wants to grow. It's even better in some sense, right? Maybe I want to make a solution to this time-dependent equation that grows. Of course, it's a bit painful. I mean, you have to track, because it means that maybe you will normalize, but at the end of the day, your renormalization was not good enough, right? And this is exactly what Herrero and Velasquez tell you. They tell you, well, but the way you're not going to construct a solution to the stationary problem. You're going to construct a solution to the time-dependent problem. And how are you going to do that? Well, you're going to do the following thing. you're going to say the following words. So this is, again, so this is maybe my renormalized variable y. And what my solution after renormalization, so this is v and tau and y, what is it going to look like? To leading order, it's going to look like phi star, which is c infinity over y to the 2 over p minus 1. So it looks like this. But then instead of trying to attach something stationary in space, I'm going to try to attach something else here. I'm going to put another boundary layer here, and I'm going to allow for another scale lambda. So it's not the same lambda, right? It's something else. So I'm going to attach another scale with typically a soliton profile here. And lambda of tau is going to go to 0. Okay, so I'm going to try to build a solution to my time-dependent equation, which dynamically will form the singular self-similar solution, right? So this is exactly the strategy. You connect something that is smooth outside the origin with something that wants to, it will always be smooth, but it will want to concentrate. Okay, so what's the point here? The point, the beautiful thing that you learn here is that this solution is unbounded. It means that this is unbounded. This is an unbounded solution of the self-similar equation. Right? And this is what people like to call type 2. Right? And there is an enormous literature now on how to do this and various settings, etc. But this picture, in some sense, which is the root picture by the initial picture by Velasquez, is an absolutely beautiful one. It's a way you say, I don't have a stationary guy to fix my equation, but I can fix it in a time-dependent way, and there is no obvious trivial way of doing this. So this has been revisited, of course, in many ways. But this is the picture. Okay, so this is something you need to learn. If you don't have a self-similar solution, well, maybe it's not too bad. Maybe it simply means that you need to look for unbounded solutions of the self-similar equation. Okay, perfect. So now all this is the 90s, I mean, essentially, and this type 2 thing is really what's been done in various problems in the last 20 years, but none of this existed in the 80s. Okay, so let me tell you about a third. Let me tell you about the third blow-up scenario that we know. It has nothing to do with any of this. So third blow-up scenario. So it looks like it, but I mean to say that now that things are better understood, it's completely different. So it's so people like to call it ODE blow-up, but it's an awful name. I hate it. It should not be ODE blow-up. This is the front singularity. And it took a very long time. It took us a very long time to understand that what is here has nothing to do with something specific to the heat equation, something completely universal. So what is this? It's the following thing. So I have dtu is Laplace u plus u to the p. Maybe I have u modulus of u to the p. And as a matter of fact, there is a trivial solution. There is a trivial solution. People call it ODE blow-up because it's a solution where you don't have space dependence. So you do something completely idiotic. You say u of t and x, you declare it's a constant divided by t minus t to the 2 over p minus 1. Okay? So you can do that. So of course, it doesn't depend on space, so the Laplace is 0, and it's precisely meant to solve this. Okay? So formally, something concentrates, but of course, there is no x dependence. So in terms of function space, it's completely ridiculous. But this solution, in fact, shows up in the following way. So this is really gigacone in the 80s. The way you can make this thing appear is the following thing. So again, just do my renormalization, lambda of t to the 2 over p minus 1 v of s and y, declare that lambda of t is the square root, and end up with, but this is my self-similar equation. It's there, so it's d tau v. I'm sorry, d tau v is Laplace v plus a half 2 over p minus 1 plus y that grad v plus v modulus of v to the p minus 1. Okay? And so this is my self-similar solution. And what I told you is that, of course, if I look for stationary solution, I have Laplace v. So maybe this is my profile is phi. So I have Laplace phi plus a half 2 over p minus 1 plus y dot grad phi plus phi to the p minus 1. This thing is equal to 0. So if I want to solve this, well, so if I unfold all this, there is a trivial solution here. There's another one, which is completely trivial. You just take, so I suppose I have a problem of sign here. There must be a minus somewhere. Anyway, well, just put, yeah, I'm sorry. Yes, I'm sorry. This is a minus. I mean, whatever. But the trivial solution is just given by the fact that you just take phi independent of x. You just take phi constant, right? So you declare that, so there is a special solution phi of y. You simply take it constant. The constant is typically called kappa. So you simply declare that kappa over p minus 1 plus kappa to the p, and there's a minus, is equal to 0, which means that kappa is nothing but something like 1 over p minus 1 to the 1 over p minus 1. Right? So this is so it is a solution to the self-similar equation. So but of course it does not decay, right? No decay. No decay. It's very weird. This guy is very funny. And you should think that the reason why people started with this equation, it's a beautiful thing, is that it's not a solution to the self-similar solution. It's the only solution, in a reasonable, smooth solution to the self-similar equation in the energy subcritical range. That is when S is less than 1. It is a fact. It's just integration by part. So in fact, all the gigacone theory was about understanding singularity formation for the nonlinear heat equation in the energy subcritical range. And what they realized is that after renormalization, essentially, blow-up solution to the heat equation are attracted to a stationary solution to the self-similar equation, but there is only one. It's only the constant. So what they showed is that after renormalization in the energy subcritical range, when this has to be, you have to locally converge to something like this. Okay, so what does it mean? It means something very funny. It means that when you renormalize things, so if this is your u, if this is u of t and x, it's blowing up, right? So it's certainly concentrating somewhere, so it wants to look like something big. Then I zoom, and what do I see? So remember u, I like to think of u as being 1 over lambda to the 2 over p minus 1, v of s and y. Maybe this is tau, I'm sorry, this is tau, and y is x over lambda. Okay, so then what does it mean? It means that when you zoom in, so maybe this is y, and now I want to draw the function v of tau and y. So what gigacone tell you typically is that, what they tell you is that after renormalization, locally in space in y, that is typically you can go till y equal 10, say, what you will look like is this constant kappa. It's a theorem. This is kappa, and maybe you're going to be, asymptotically, if you wait long enough, you're going to be a small perturbation of this constant kappa. But it's a description, of course, that's really local on the singularity. So it's really telling you what's happening here, very close here. But you know that you cannot be the constant kappa forever, right? Because you started from a true solution. I mean, this being typically in x, you can think that it has decay in x. So you cannot stay close to this guy forever. It's really constant. Okay, so it is necessarily for this picture to be true, there has to be a region where dynamically Right? There has to be a reconnection region. Okay, so in other words, there has to be a zone in space. So you should think that maybe this is y. So maybe 1 over lambda of t is here. So here you are out of the singularity. Right? So really there has to be, so you can maybe be this constant kappa, but you cannot be this guy forever. There has to be a region in space where something has happened and where you will reconnect to something that wants to decay. It's necessary. But again, interestingly enough, the gigacone analysis arrived there not by studying this, but really by directly looking at all solutions and understanding that locally on the singularity, you need to converge to a stationary solution. And in fact, there is only one in the energy subcritical range. So the analysis of this reconnection region, of what happens here, and of whether it's universal or not, is something that was done by Franck and Atemzag, and also Bricmont and Kuptianian. And let me tell you, so if you want to read something here, I invite you. So it's really there is this Melzag paper at Duke. I think this is 94, 96, I don't know, 94 something. You want to read the introduction of this, and they explain you exactly what's going on here. So I think, yeah, actually, I've written this here. Yeah. So how are you going to do this? So how do you do, so this is what I like to call, this is the front singularity. And there is a very simple idea here, which will be central for what we're going to do. So it's very clear. So I want to solve this. I want to solve deta v equals Laplace v. So there's probably a half. Yeah, I'm sorry. Of course, there's a half. So it's minus a half, 2 over p minus 1 plus y dot grad v plus v vp minus 1 is equal to 0. Okay? I want to solve this. And I want to have something. I know what I want. I want to solve this PDE. So this is my inner PDE. But I'm supposed to look like a constant for a very large region in space y. So it's very clear. So it simply means that you're not at the right scale. Okay, so you have to change scale. Okay, so you change scale again. So you declare, so you let z say, so what did I put? I put square root. So I put b. So you declare z to be, you make a change of variable again, b of s times y. Okay, and you look for a solution. So I mean, this is a tau. And you look for a solution. So you want v of tau and y. I don't know, you call it bv, big V of tau and z. Okay, so you scale again. You say, I'm not saying the right scale. Okay, so let's compute the equation for v. What's happening here? Well, okay, so what does d tau do? So d tau v, so what I need to do, so I have d tau big V. I did not change time. And remember, z is by. So I'm going to have, so if I by, I'm going to have, so if you just take the derivative, so I'm going to have beta, remember this is dot. I have beta y, if you want, dz. But of course, I like to think of it this way. I like to think that z is by, so this is just, there's a v, so this is just d tau plus beta over b z dz. Exactly. Okay, so this is the first term. This is how deta acts. Okay, so what about my Laplace? So Laplace v, oh, but that's very simple. So I have to be careful. I change scale. So this is Laplace in time. So z is by. So I'm going to have b squared Laplace v. Okay, after the change of this is in y, this is in z, right? This is understood. Okay, and then I need to look. So now the key, of course, is that scaling does not see this. 1/2 2 over p minus 1 plus y dot grad. You see, y dot grad does not see that you change the size. So this is unchanged. This is 1 over 2 over p minus 1. This is, if you want, this is z dz in this case, big V. Okay, and of course, v to the p does not sit because I did not change the size. I've just let it be. It's v to the p minus 1. Okay, so what equation do I get? I get something very simple. I get something, yeah, perfect. I get something very simple, so I get the following thing. I get exactly, so I get delta v plus beta over b z dz v equals b square Laplace v. So I have minus 1/2 2 over p minus 1 plus z dz v plus v to the p. I have this. Okay? So now question, do I have a simple solution to this? You understand what I'm looking for? I'm looking for something that's spreading. So I'm looking for b of tau. I want b of tau to go to 0. That's what I'm looking for. And let me assume, so that's part of the analysis, so because this is unclear, it depends. But typically what you will find in the Melzag is the so-called stable regime. So it's the case where this guy is ignored. So I will assume that beta over b actually goes to 0 as tau goes to infinity. That's an assumption which I will need to check at the end of the day. So it means that asymptotically, what I feel like doing, so I want to ignore this term. But more importantly, I want to ignore this one. Okay, this Laplace term, in some sense, I want to think of it as being weak. I ignore it. Okay, and I ask myself, do I have a stationary solution to this equation now? Can I just solve this? Can I solve 1/2 2 over p minus 1 plus z dz? So this is, if you want, this is z v prime equal v to the p. There's a v here. Sorry. It's the operator. Exactly. Okay, and the answer is yes. In fact, you have tons of solutions to this. So I think I've written this here. So so it's exactly it. So in fact, you have tons of them. So you have kappa. So you should think of it this way. So you have 1 plus c0 z square to the 2 over p minus 1. Okay, well, kappa is precisely the constant that you had before, and a priori, this parameter here is free. At this point, it's free. Okay, so what does it mean? It means the following thing. It means that if you look at this problem here, there's a first order. You know, if you change, that is, the philosophy is exactly this one. It's, you know, type 1 means self-similar scale is good. It shows you the right object. Type 2 means unbounded in the self-similar normalization. Something gets huge. ODE, or front, means yet something else. It's not that I'm not getting large. I mean, of course, it's a question of norm, but nothing gets large. I mean, it's just about making a connection from kappa to something else. So it's a connection problem. It's a connection problem. But you cannot address it. But if you want to see it, you need to change variables. You need to put yourself at the right scale. You see exactly what's going on with the function. You know, z is by. So of course, when y is of size 1, b is going to 0. So z is super small. So what you're seeing is just kappa. That's exactly what you want. That's your constant. But of course, when you go further away, you start seeing, so typically, when y is of size so z, so when z is of size 1, so y is of size 1 over b, you start seeing the connection, and then the heart of the matter is to compute this law. And so now, if you want, the analysis now is what is the law for B of tau? What is B of tau equal to? Okay, so it means, so if I want to summarize, this is perfect. I have about half an hour to conclude. So what's the conclusion of this? It's the following thing. For the focusing heat equation, and this is something that has been propagated and revisited in many ways by many different authors on many problems, and this is a picture that really has emerged in many problems, you have three situations. Either, well, the simplest possible thing you can have in your hands is just a self-similar scale. This is type 1, you renormalize self-similarly, you pick a stationary solution with a good decay. If you can construct it, good for you. That's the simplest possible situation. But if this does not hold, then there are two different kind of mechanisms that we can think of. Type 2 means, well, don't look for bounded solution, look for unbounded ones. Front means, well, you renormalize self-similarly, but you're still not looking at the right scale. You have to understand how to change variables again. And then something very interesting happens in this setting is that when you look at your equation, typically, and that's the heart of this kind of front singularity, this kind of renormalization comes by weakening the Laplace term in your equation. It's embedded in the change of variables. Okay? So what will be, and maybe I should start this now. So what's the philosophy? What's the philosophy? So a strategy to understand, to construct a blow-up scenario for defocusing NLS is exactly this one. Is exactly, so the strategy that make this completely explicit is we're going to blend type 2 and front. You need to understand that you don't, it's typically, I mean, all these problems, of course, there are no self-similarity. Type 1, you can forget it immediately. It's very clear that it will never work. But this complicated scenario, they're just examples, and in fact, they're just telling you that there are canonical ways. Another way of saying this, what you want to do, your obsession, is to try and reduce the self-similar equation, which in general is complicated. You want to try and reduce it to a simpler problem. And that's exactly what both the type 2 blow-up a la Velasquez or the front scenario here that is described here do for you. Try to reduce to a leading order simpler equation. Right? And then, of course, I mean, even if you can do that, when you're just getting started, right? You need to understand how you can make all these theorems and close estimates, etc. But I'm not even talking about this. I'm just talking about the formal picture. How can you actually even just formally understand what's going on here? Okay, so let me show you this. Let's take the time to do this computation. So I think I've written this here. Yeah. Let's just try to do this together. So I think I've done this. Yeah, excellent. Okay, so let me go to the heart of this series of lecture now, because I think now I can do what I want to do, and I think it would be much more clear why I'm doing this. So I really want to talk about defocusing NLS and stick to it. Of course, it will come with compressible fluid, obviously. Defocusing NLS and compressible fluids. Okay, so it's the same. The equation looks very much the same. So I dt is Laplace plus, so it's a minus now. So actually, I'm going to put plus and minus here. Okay, so I want to form a singularity for this. And I know, so again, u of t and x is complex valued. And I will have a blow-up time, which is going to be t, which is going to be finite. And it's not in, what am I saying? It's in C, I'm sorry, X is in RD, and T is my time. Okay, and what do I want to do? I want to form a singularity for this thing. So following exactly this intuition, I know what I have to do. First thing I do is I renormalize. So everything I'm going to talk about, which is of course an important simplification in the problem, I will always assume that U has radial symmetry. Right, so really my vector field, so X is really, I'm going to think of it as being R. Okay, so everything, there's no gradient, right? It's always the derivative in R, always. Okay, so first thing I want to do, I want to write the self-similar equation. So the self-similar equation, so I'm just going to renormalize exactly like I did. So I'm going to have 1 over lambda of t to the 2 over p minus 1. I have v of s and y. And maybe for NLS, it's not too bad. Actually, this is I can do it if I want to. So I'm going to have maybe I can put a phase if I want to, but this is irrelevant. It's just because this is the classical way to change variable. And y is x over lambda, and ds d tau is 1 over lambda squared. Okay, and then I get my self-similar equation. So it maps my flow explicitly. So it maps my flow explicitly onto the self-similar equation. So I'm going to have, it's exactly the same rule of the game. So I'm going to have I d tau v. So I'm going to have, so it's a minus, right? Yes, exactly. So I have, so the scaling variant part does not change. So I have Laplace v, I have minus v to the p minus 1. And then what do I have here? I have, so when I dt, I'm going to have gamma dot. That's going to come out here. So I'm going to have minus gamma tau v. So remember, when I note tau, when I say gamma tau, it's just d gamma d tau. And then, of course, I need to hit scaling. So I have minus and I have an I. So I have minus I lambda tau over lambda. And lambda tau is just d lambda d tau. And I have 2 over p minus 1 plus y dot grad v. And this whole thing is equal to 0. Okay, and I don't even want to think about it. I really do the standard renormalization. So I just take lambda of t to be the square root, which means that minus lambda tau over lambda is just 1/2. Okay, so in fact, I mean to solve my self-similar equation is just I d tau plus Laplace minus gamma tau. So I think did I take? Well, I'll choose it later. Minus gamma tau v. So I have plus a half 2 over p minus 1 plus y dot grad v minus v. Did I put an I here? Minus v to the p minus 1 is equal to 2. Okay, this is what I want to solve. So I want to understand, my aim is to build a global solution in time of this equation, which does not disappear. Okay, and I'm really just going to construct one. Okay, so let's see. So ignore the phase term. It's irrelevant. Don't think about this guy. So if you ask yourself about what we've done before, you see, if you want to try to make a self-similar solution for this equation, just look for a stationary solution here. It's certainly expected that because of the sign, this is not going to work. You can probably turn this into a theorem. So type 1, you forget it from scratch. If you want to make type 2, remember type 2 is based on so the self-similar solution is actually no. So the phi star is gone as well, right? It's because of the sign here that will not agree. So it doesn't seem to be very efficient. And the constant solution if you want to try to make a v constant, like to have a some kind of a front, you see if v is constant, people try to do that, but you see the problem is that then it's telling you that v modulus of v is equal to I times v itself. You have a problem. You have a modulus that's complex. It's not going to work. So in some sense, the trivial scenario that you know, it's just two things immediately, nothing is going to work. But all you need to say is the following thing. So, the question is, can you look for unbounded solution at a different scale? That is, you should think of it this way. What I want to say is there, after, I know this is type 2, this is from, I know I need to change variable again. Is there a canonical way? So what I want to do is I want to change variable in a canonical way. And of course, what I want not to destroy my equation. I want not to ruin it, right? If I send after, I need to simplify it, but I don't want to throw it to, I don't want to throw everything to the garbage. So I want a simplified leading order equation. But of course, I don't want something too simple. And in fact, I know exactly what I have in the back of my mind. I need a connection. I need a connection profile. That is, I need exactly the analog. Well, so I erased it. So this magic function for the heat equation, the constants over 1 plus z squared to the 2 over p minus 1, that's the guy I'm looking for. OK, so you try. You play with renormalization and etc. We could not do it. So if you try here, we don't know how to do it. So you have to do something first. And it's not like, we could not do it. We could not do this directly on star, if this is star. You need to do something before. You need to pass to hydrodynamical variables. Okay, so there is something here that is extraordinarily annoying, but we are not able to see the nature of the simplified equation here. If you want directly on the complex number v, or if you want directly on the system of real and imaginary part, we need to pass to hydrodynamical variable. So it's a very simple thing. Of course, if you assume that v does not vanish, etc., which will be part of the analysis, you can always declare that your complex number, you can always write it down as a phase and a modulus. Okay, so the modulus, I'm going to call it omega, and you plug in omega into the I phi. Okay, so phi, so omega and phi are real value. So you fit this. Well, how much I know? So maybe let's do this quickly. So if you fit this to the equation, you understand what you have to do. What you have to do is you just need to compute derivatives here. And of course, because omega and phi are real valued, and because your nonlinearity, you see, it has a structure. It's v modulus of v to the p minus 1. So at the end of the day, you can always factorize the phase. You will get a system of two equations for tau of omega. So let me skip to this. So I get exactly this. I get the following system. So this is d tau omega is minus Laplace phi. So what do I get here? Plus 1 over p minus 1 omega minus, so I have the following thing. I have twice dy phi divided by y plus 1/2 lambda omega. And I remind you that lambda is y dy. It's the scaling drift. So this is the first equation, and for the phase, I have omega dt phi is equal to Laplace omega plus minus Laplace phi squared minus gamma tau minus a half lambda phi, the whole thing as an omega, minus omega to the p minus 1. Okay, so this is the equation. This is the self-similar equation written in hydrodynamical variables. Okay, so what are the rules of the game? It's very simple. The rule of the game are the following. This is too complicated. I don't know how to deal with this. So I want to simplify this guy. So what I'm going to do for you, I'm going to make a transformation of this equation, which is going to give me exactly the same, except one term. Okay, I'm going to kill, I never know which one. I'm going to kill one of these two Laplace. I'm not going to kill them all. This is exactly why I don't know how to see things at the level of this equation, because I'm not going to kill the Laplace like like for the heat equation. I'm going to kill part of it. Okay, so I'm going to transform this, and after the transformation is done, I'm going to see exactly something very similar, except that there will be a small parameter in front of one of these guys. Okay, so I'm going to have almost the same equation modulo one term. Okay, so let's just do this. And this is really, you understand, the reason why you want to do this is exactly because you're looking for something that's like a type 2 front. This is exactly the philosophy behind this. So what does it mean? So I'm making an ansatz. So actually, I think I wrote this here. Exactly. But I need this page too. So of course, this is where you start entering fun and numerology. Okay, so what's the ansatz? So it's very clear. So omega is my phase. So I'm going to ask for something that's like type 2. I want to be unbounded. I want something to grow. Okay, so I'm going to ask omega of tau and y to be like, I'm going to allow for growth. So I'm going to put 1 over square root of b to the 2 over p minus 1. And then I'm going to put a function which I call rho of tau and z. But z, so I'm going to tell you what phase is. So z is like a front. So did I put b or square root? I put square root. So b is y square root of b. Okay, so b is a function of time. Huh? Okay, so you understand it's exactly like for the heat equation. It's like I'm looking for a front. I'm changing scales, but I'm allowing for growth here. Okay, so this is how modulus is supposed to evolve. And my hope is that this renormalizes the new variable rho. And for the phase, I do exactly 1 over b psi of tau and z. Okay? And then you fit this this is too far. Okay, so I think I've written this here. So I think we can do this computation here. We just have time to do this computation together. Okay. So let's just do this together. What will the first equation tell me? Okay, so I'm looking at this here. So I have 1 here, I have 1, I have 2. Okay, so you see there is a point with this transformation is that there is a complete here. It's the one that doesn't change anything. So okay, I'm sorry. I need to assume something. I anticipate. So I will declare that b tau over b is minus e. So e is a number. So it needs to be positive. So if you want, it just means that in tau time, which remember is a global time, I'm asking for exponential smallness. So of course, e is a terrible notation, but that's the one we have. So I'm exponential minus e tau. Okay, e has nothing to do with e. Okay, that's the way it is. So beta over b is minus this constant. So I need this thing to be positive. So I anticipate it. I enforce it from scratch. Okay. So let's compute theta omega. So this is not too bad. So what is going to be theta omega? So what do I have? So I have my normalization in front. So I have 1 over square root of b to the 2 over p minus 1. Okay, so I certainly have theta rho. Now it's a logarithmic derivative with respect with what I have in tau. So what I have is exactly, so I have my operator So I'm going to have, so because I have a half and beta is b, so I have minus, so I have plus e over p minus 1 rho minus a half e lambda 0. Okay, so this is what I get when I take the derivative here, and the derivative here. Okay, and the sign is because one is negative and the other is positive, right? Because one is beta. This will see minus. Take a logarithmic derivative, and this will see minus beta over b, so plus e. So plus e. This will see plus beta over b, so minus e. Okay, so one is positive, one is negative. Okay, so this is theta. Okay, and so this is supposed to be equal to what? So theta omega is equal to. So let's do Laplace of phi. So what do I have? I have 1 over b. I'm sorry. So I want to put in factors. So look at what I have here. So omega renormalizes with the 1 over square root of b to the 2 over p minus 1. So I have 1 over square root of b to the 2 over p minus 1. Maybe times rho if you want. This is just my omega term over there. So Laplace phi. So remember, phi is 1 over b, but you have to be careful. Laplace. It's like for the heat equation, the Laplace, I have y square root of b. So when I take two derivatives, I'm going to pull out the factor b. So I have b Laplace of what I call psi. Okay, so this will cancel. It's meant to be. And then I have minus, so I have in here, so I have minus twice. Okay, so when I take dy, it's cost me a square root. Then I divide by y, but y is z over square root of b. So this is z over square root of b. And then I have, then I have, of course, I need to take dz of phi, but this is 1 over b. So I have 1 over b dz psi. Okay, so this is the term dy phi over y plus 1/2. So I have plus 1/2. And then the square root of b, so I have this omega factor. And of course, lambda does not see scaling. So I have lambda rho. OK, so you see what's going on here. This equation is perfect. It's precisely how we come up with it. It's the scaling. You should think it's the scaling that killed the equation. So the only thing that time dependence adds is this term here. Right? This is generated by the fact that my b is allowed. So it's this term here. I don't have color. So this term here sees the fact that b is allowed to depend on time. But otherwise, if you want, it's a scaling symmetry for the first equation. OK, so we get exactly. So it means that my first equation now has become exactly this. So I have exactly theta rho. So I'm going to write it here. So this is my new guy. So this is theta rho. Is because I multiply here by rho. So if you trust me, you get exactly this. You get minus rho Laplace psi minus e plus 1 over p minus 1 rho minus, I can write it like this. I have twice dz psi plus 1 minus e over 2z, and the whole thing is dz rho. Okay? So in some sense, think that it's really a scaling. It's like this equation has a scale. I didn't lose anything. Actually, it's like I added a term. This is the first equation. No smallness. I haven't done anything. The interesting thing is what happens to the second equation. So the second equation. So what do I get? So let's just do this together. So what do you have? I have omega d tau phi. So omega, so it's 1 over square root of b to the 2 over p minus 1. Omega is rho. And now I need to compute d tau phi. But of course, this is easy. So I put 1 over b in factor. So I have d tau psi. And then I have plus e psi, because this is the 1 over b term. And then I need to remember that space is changing as well. So I have minus a half e lambda z psi. Okay, this is the fact that space is dilated. Okay, so this is omega d tau phi, and it's equal to what? it's equal to Laplace omega, but Laplace omega is 1 over square root of b to the 2 over p minus 1. And then here, something happens. I'm taking two derivatives, so here I have a b. I have b Laplace rho. Okay, and then I have minus, so let's see this. So what do I have here? I have a grad phi squared, so I have, exactly, so I have, so grad phi squared, so I have 1 over b squared, but I've put a square root, so the gradient comes with the square root, but I'm squaring it, so I have b grad phi squared. Okay, and then I have this gamma tau. So I'm sorry, I need to declare, I will declare that gamma tau, what did I choose? I think I chose one, I declare that gamma tau is minus 1 over p. I can always do that. So I have minus gamma tau, so I have plus 1 over b. And then I have minus a half, so lambda doesn't see scaling. So I have, I'm sorry, so this is lambda phi. Yeah, so this is trivial. So phi is just 1 over b, so I have minus 1 over b lambda z psi. Okay, so everything scales the same way. Then I multiply by omega, which is 1 over square root of b to the 2 over p minus 1 times omega, which is rho. And then I have minus, so this is meant, I'm sorry? Lambda z, yeah? It's z dz, right? So this was lambda y. It's lambda, right? Lambda, when I write lambda, it's just scaling. So here it's y dy. Okay, but the point is, you see, y dy, when I change variable, it's z dz. It's an operator that doesn't see scaling. Okay, so the 1 over b there just comes from the fact that phi itself comes with the 1 over b in factor. But the differential operator does not see it. Okay, so I have 1 over b here. Then I have 1 over square root of b to, that's my omega. That's this term here. And then I have omega to the p minus 1, which is exactly meant to be, this is exactly meant to be 1 over square root of b to the 2 over p minus 1 times 1 over b rho to the p. Actually, I will, oh, okay, I can put rho to the p. I mean, actually, rho is positive, so I have rho to the p, right? Because this is, it's meant to be. It's the choice of 2 over p minus 1. Okay, so what can I do? I can simplify. So let's see. I have one, you see, I have this, everybody has this guy. Everybody has 1 over b, 1 over b, 1 over b, 1 over b. But this guy has b. So when I'm going to come back, what I see so what I find in the end, so if you want my system, so I get exactly this. So the second equation becomes, so you check it out a little bit, but you have exactly this. You have rho d tau psi equals, so you have b squared Laplace, I never know, rho, minus grad psi squared where did I put it? Of course, I changed because I defined, so I suppose I can read it off from here. It's just that, yeah, so I have minus grad psi squared. I suppose I have over there the plus 1. I have minus lambda z psi, and this is multiplied by rho. And then, but then what I'm missing, I'm sorry, what I'm missing, yeah, there is a numerology here. What I'm missing is this term. So in fact, at the end of the day, what you can show is exactly this. So you have exactly, I'm going to write it exactly. This is the formulation I want. So I have b squared Laplace minus, exactly. So this is plus e psi. This is the term from the d tau, minus 1 plus 1/2 1 minus e lambda z psi plus rho to the p minus 1 multiply rho. Okay, this is what I get at the end of the day. Okay, this is what you get after renormalization. Okay, so this is exact. So this transform, this is nothing but an explicit transformation of the equation. So this is the equation 2. And if you want, all I've done nothing more. All I've done is this. I've defined this. Okay, so I have enforced b of tau to decay to 0 in the way that I want, so minus e to the minus this parameter e tau. Okay, so now, and this is where we'll start next time. If you remove this term, this is compressible Euler. It's not an approximation, it's exact. It's compressible Euler written in self-similar variable. I will show this next time. Okay, so if you get rid of this term and only this one, you have an equation. It's the fluid, it's exactly the classical fluid equation. So this is the heart of the analysis. Think of this term as being a perturbation because b goes to 0. Understand singularity formation for this problem, which is verbatim compressible Euler, and then come back and show that you can close with this as well. Okay, so this is what we will do in the next 2 classes. Understand the key steps. What are the difficulties? What is the structure? And more importantly, what for me is really fundamental is to show you 2 phenomena that we've seen on the heat equation: supercritical numerology, some need of spectral analysis, and how, supercritical numerology, and how spectral analysis forces you allows you to understand whether or not some objects exist, in particular some nonlinear structure are there or not. This is elementary in some sense, or very well understood now on the heat equation. It's not that elementary. Actually, you had to work for this. It's going to be crystal clear on this problem as well. Okay, thank you.
Merci pour cette deuxième lecture. Alors, des questions, des clarifications.
La dernière fois, tu nous as dit que c'était une équation en rho et gradient psi.
Oui, absolument. Ça, c'est Bernoulli. Excuse-moi. Ça c'est Bernoulli sur l'air compressible radial. Tu vois, quand tu as un champ de vecteur, quand tu as eu gradient U et que tout est à symétrie sphérique, c'est vraiment dr u carré sur 2. Donc en fait, ton équation de l'air, elle a une intégrale première. C'est Bernoulli. Donc en fait, là, tu as l'intégrale première. C'est le premier truc que je vais faire demain. Je vais prendre une dérivée de cette équation. Donc effectivement, la vitesse U, c'est vraiment gradient psi. Et qui, dans mon cas, est vraiment dr psi. Ça c'est Bernoulli.
Oui.
D'où, Guillaume, vous est venue l'intuition d'utiliser hydrodynamique equation?
C'est une excellente question. Non, mais il y a aussi le fait que, par exemple, moi j'ai été très influencé, magnifiques travaux de Gravja et Smets, par exemple, sur les solitons pour Ginzburg-Landau, et justement comment ces variables hydrodynamiques te permettent de voir des choses. Alors, sur leur papier à eux, c'est intéressant, ils ont d'abord fait des choses en variables hydrodynamiques, après ils sont revenus, ils ont été capables de redémontrer les choses dans les variables originelles, mais c'est le fait que ces variables soient pertinentes, c'était quelque chose qui était compris. Après, les ansatz semi-classiques aussi, il faut le dire, ce que les gens ont beaucoup fait sur ces équations-là, par exemple, il y a des travaux de Lobo qui sont liés à ces choses-là, c'est d'essayer de construire des paquets d'ondes pour lesquels on va démontrer typiquement dans le cas supercritique qu'on n'a pas d'uniformité du flot ou des choses comme ça qu'on va essayer. Et c'est typiquement des ansatz qui sont construits. Tu vois, j'ai fait une phase semi-classique là, c'est-à-dire j'ai forcé ρ e i psi sur b. D'accord? Donc on est totalement dans l'enveloppe convexe. Faire un ansatz semi-classique sur NLS, c'est exactement faire ça, sauf que ce que font les gens typiquement, c'est que b est constant. Donc il résonne avec un b petit, mais fixé. Et ça, c'est juste le epsilon carré psi qui est là, c'est juste la variation, c'est le h bar de Laplace typique. Et ce qu'on va faire, nous, c'est qu'on va, on n'a pas un ansatz semi-classique avec b petit fixe, on va envoyer b en temps à 0. On va vraiment tenir la solution dans son régime semi-classique jusqu'au bout, c'est le but. Donc il y a écrire NLS en variable hydrodynamique, il y a plein de gens qui l'ont fait avant nous. Ça a donné plein de choses. Peut-être ce qu'on a fait, nous, c'est qu'on a cru à ces variables jusqu'au bout, notamment jusqu'au bout en temps. Voilà, on ne s'arrête pas et on va jusqu'au bout et on croit en cet ansatz jusqu'au bout.
Mais oui, je me souviens, à l'époque, il y avait eu l'étude de la limite classique de NLS vers Euler, compressible, donc c'est un travail d'Emile Grenier. En fait, ce qui était important, c'est de faire la décomposition de la fonction d'onde, ρ puissance θ, mais en gardant une partie imaginaire dans ρ. C'est de ne pas prendre ρ entièrement réel. Ça, il n'y a pas de chose comme ça, oui. C'est en fait de garder un petit morceau de phase.
Non, on va vraiment pas faire ça, et je te dis, on va vraiment dire que ça, c'est Euler compressible. Et Euler compressible, c'est Euler compressible. Non, c'est
pareil, mais en fait, de garder un petit morceau.
Non, on ne garde pas, mais une fois de plus, si tu veux, c'est pas. Nous, on n'a pas un epsilon, et on n'a pas une solution qui dépend de l'epsilon. Le epsilon, il est dynamique en temps. Voilà, donc c'est pour ça qu'on peut faire des choses que peut-être que tu peux pas faire dans d'autres. Mais c'est exactement ça qu'on va démontrer, c'est qu'effectivement, tu peux croire en cette équation comme étant la partie principale de celle-là. C'est le but.
Oui, là, je suis d'accord.
Mais donc, non, on garde ρ est réel, et on ne garde pas de...
Alors, sur cette équation, où est-ce que tu vois focusing et defocusing?
Ah, c'est une super question. Tu ne le vois pas du tout. Si tu étais defocusing, tu aurais un moins là. Sauf que, du coup, c'est plus Euler compressible. C'est autre chose. Mais le principe, tu auras autre chose, mais tu pourrais tout à fait étudier. Et c'est très intéressant. Et en fait, il y a plein de... En fait, je te montrerai.
C'est une équation elliptique espace-temps, en fait.
Je sais pas, tu changes...
Enfin, quand c'est plus Euler, quand la pression a la clé du son imaginaire, ça devient une sorte de système elliptique en espace-temps. Puisqu'en fait, ça revient à minimiser une fonction convexe, en fait.
C'est parce que tu le penses comme ça, mais moi, je ne le pense pas comme ça. Moi, je le pense totalement en termes d'état stationnaire. Est-ce que je sais faire des états stationnaires de ce truc-là? Alors, si c'est Euler, si je suis défocalisant, c'est Euler, et ça, c'est la réponse à laquelle on va répondre demain. Si c'était focalisant, c'est pas Euler, c'est quelqu'un d'autre, mais on peut aussi en faire, aucun problème. Le gros problème que tu vas avoir, c'est quand tu vas commencer à regarder le linéarisé. Tu as des gros soucis. Lui, il pousse plus pour toi, il pousse contre toi. Et donc c'est ça qui est étonnant, c'est qu'en fait, c'est dans le cas défocalisant, c'est plus simple. Ça pousse pour toi. C'est-à-dire que lui, tu comprends bien, c'est le plus grand nombre de dérivés dans l'équation, tu ne peux pas le laisser à droite. Il y a un moment, il va falloir que tu le remettes à gauche. C'est pas une perturbation de l'équation, ça. Tu vois, c'est pas B carré ρ, c'est B carré Laplace ρ. Donc quand tu vas le remettre du bon côté, il faut qu'il pousse pour toi. Et ça marche parce que tu es défocalisant. Si tu changes le signe, gros problème.
Non, mais enfin, dans mon souvenir, quand même, le lien focalisant-défocalisant. Alors bon, effectivement, là, le fait que B c'est dépend du temps sur notre histoire, non, ça se lit sur la pression dans la transformée de Maglung. Donc,
mais c'est là, hein, le seul endroit où tu vas voir, c'est unique. Ah, je sais pas, mais enfin.
C'est vraiment la pression dans la transformée de Maglung.
Voilà. Il est là le. Je crois que ce que les physiciens appellent la pression quantique, c'est aussi ça, là.
Non.
C'est encore autre chose. Ah voilà, voilà, c'est ça. Parce que je crois que la pression quantique, c'est ce machin-là.
Oui, la pression quantique, c'est le terme en laplacien qui est là.
Voilà,
je parle de la pression.
Voilà, non, tout à fait. La pression, c'est exactement ça. Tu vas changer, c'est ρ puissance gamma, c'est exactement ça. Tu vois le focalisant, défocalisant, exactement sur la pression. Tout à fait, parce qu'une fois de plus, c'est Bernoulli. Donc, mon gradient P, je l'ai intégré. C'est pour ça que tu vois ça, c'est ρ puissance gamma. C'est la pression. Tu dis, le premier truc qu'on va faire demain, on va prendre une dérivée de ça.
Oui, donc en fait, pour clarifier ce que tu dis, excuse-moi, dans ce sens-là, en fait, on ne sait pas faire la chose dans le cas focalisant. Oui. La stratégie ne marche pas.
Oui.
Si ce n'était pas clair dans la réponse, c'est pas il y a des choses qui ne marchent pas, c'est qu'on ne sait pas le faire. Hein.
C'est un peu plus tordu que ça. C'est-à-dire que je vais répondre à la question demain, comment on construit des profils stationnaires? Moi, on saurait le faire dans les cas focalisants et défocalisants. D'accord? Par contre, les transformer en solution du problème complet, on sait faire côté défocalisant. On ne sait pas faire de l'autre côté. Il y a un très sérieux problème. La pression quantique, comme tu dis, elle ne pousse pas pour nous. Il y a un sérieux problème. Ce n'est pas forcément insurmontable, hein, mais tel quel, ce qu'on écrit ne marchera pas.
Oui, en fait, c'est relié à la question que tu disais au tout début, hein, de mon point de vue. C'est qu'en fait, on peut faire des tas de solutions formelles, mais après, la fin, c'est qu'il faut fermer tout pour en faire des solutions. Et ça, c'est jusqu'au bout.
C'est jusqu'au bout.
On doit tenir là-bas.
Mais est-ce que c'est l'équivalent de ce seuil dans les solutions Ah oui, ce seuil, c'était uniquement pour les types, les solutions de type 1, c'est la constante de Hardy-Joint.
Ouais, tout à fait, fondamental.
Il y a quelque chose d'équivalent dans...
Alors je vais te montrer de manière là. Donc on va poser exactement la question si tu veux. Là, la question avant c'était la constante Joseph-Newman, c'est est-ce qu'il y a des solutions autosimilaires pour la chaleur. Donc maintenant, est-ce qu'il y a des solutions autosimilaires pour l'air compressible? Tu vas voir que la numérologie, elle est partout, et qu'il y a un analogue complet qui va sortir, qui va exactement nous contraindre la dimension, la non-linéarité, etc. Tu vas le voir surgir tout de suite.
Bien, s'il n'y a plus d'autres questions, merci.
Merci.